Hello, I'm Fiona, and I'm a geologist, and I've been working on understanding the rocks in the subsurface for over 25 years. Today I'm responsible for leading the site investigations for GDF in the UK.
We have been asked to give an update to the Copeland Community Partnerships on the work we are doing at NWS to understand the geology of the inshore area off Copeland and why the evidence demonstrates that there are rocks that are potentially suitable for a geological disposal facility, or GDF. The inshore area lies between the coast and the limit of territorial waters, which is around 22 kilometres from the coast. This area is the focus of our geological studies at NWS. The geology is a very important part of keeping waste safe for the long term. And by long term, we mean the hundreds of thousands of years after closure that waste will need to remain safe and not cause harm to people and the environment. To protect people and the environment, the geological disposal facility will need to do two things. Firstly, it will need to isolate the waste from people and the environment in the right rock at the right depth. Secondly, it will need to contain the waste by using its geology to slow any movement of fluids. The geology plays an important role in long-term safety. If we want to isolate and contain the waste, we need a suitable geology and a compatible system of engineered barriers.
To evaluate the long-term safety of a site, we need to understand the site and its geology, both today and in the future. To do this, we start undertaking studies that give us the information engineering and safety case assessment technical experts need to perform their assessments. The process of evaluating the site and the rocks is a cycle, and there are 3 steps to this. Step 1. The cycle starts with geoscientists working with end users like the engineering design and safety case experts to work out what questions need answering as we move forward. The geoscientists then work with the experts to identify the information they need to answer the questions and use that to design data gathering activities such as drilling, testing, analysis, etc. Then we kick off these studies and start the process to gather the data. Step 2. We process and analyse the samples and integrate all of the data and information into a knowledge base. We then use that knowledge base to interpret our findings to get the most up-to-date understanding. Step 3. We present our findings to the engineering design experts and safety case experts in many different ways, so that they can assess the information, work out what questions still need answering, and any further data and information they require. The cycle then starts again. It's important to note that the geologists don't decide on the suitability of a site. They work to build a picture of the geology to help the engineering design team to develop a solution. It also helps the safety case team to assess the ability to make a GDF post-closure safety case. So where are we in that cycle today? We are working towards the end of our second cycle, which is focused on understanding the properties of the rocks in the Mercian Mudstone group. And we'll then put our findings through a rigorous evidence-based assurance process. I'm now going to hand you over to my colleague Jason, who can go into more detail about how this works.
Hello, I'm Jason. I'm a geologist. I've been working as a geologist for more than 25 years, and I'm part of Fiona's team, and I'm responsible for the geological evaluation of the sites that we are investigating. Fiona has very nicely described some of the work that we've been doing over the last couple of years and how we do it. Now I'm going to talk about the results of our work and show you some of the implications and what that means for us. So let's start by reminding ourselves of the Inshore Copeland 3D Seismic Survey. NWS ran its first ever seismic survey off the coast in Copeland in August 2022. That meant We had a vessel in the water, the Shearwater Bly, and it spent about a month collecting 250 square kilometres of high quality inshore 3D seismic data in the polygon shown on the map. We started processing these data in September 2022, and it took us about 9 months to complete the processing. Seismic surveying is the technique we use to image the subsurface with sound. It works in the same way that bats and dolphins use sound waves to see. They emit a sound pulse which bounces off buildings, trees, or even the ocean around them, and they use that reflection to build a picture of their environment. Our seismic data does the same thing. We use a vessel in the water which emits a sound pulse. That sound pulse travels down through the sea and into the rock. The pulse then bounces off boundaries within the rock, which shows us where the rock properties change. That helps us build a picture of the subsurface. This is a 2D seismic line. You can see where the seismic line is located on the map. The seismic line runs from the southwest to the northeast nearer the coast. This is a pre-existing 2D seismic line, so not from the NWS survey, but it's a great example of how seismic data can look. The x-axis shows that the line is about 15 kilometres long, but the y-axis shows the time that it takes for sound waves to travel into the earth and then reflect back up. We can see that it takes about 1700 milliseconds from the sound at the bottom of this line to reflect to surface. On this section, there are lots of black lines. These black lines show us when and where sound pulses bounce back within our seismic data volume. They're called reflections, and they tell us where the subsurface rock properties change. By bringing together the seismic data with other data types, like borehole data, we can begin to interpret these reflections and build a picture of the geology. On this line specifically, we've interpreted a couple of horizons or changes in rock type. We draw your attention to the part of the top of the section where we've interpreted a blue reflector, which is the base of the Mercian Mudstone group, and then we've interpreted above that a red reflector, which we call the top of the Mercian Mudstone group. So we can see within this seismic section the area that we interpret as Mercian Mudstone group. The Mercian Mudstone group is the rock we hope could accommodate a potential geological disposal facility. It's a well-known rock type in the Inshore Copeland area. It outcrops, or in other words, it's visible at the surface all across the UK. The picture on the slide shows an outcrop of the Mercian Mudstone group near Bristol. It's a cliff section just under the Severn Bridge, about 10 metres high, and you can see that the Mercian Mudstone is a red-coloured rock type. The image on the right is called a stratigraphic column. It shows different rock types in the Inshore Copeland area. The Mercian Mudstone group is shown at the top of the section, and you can see that the Mercian Mudstone group is actually a mix of different rock types. It's primarily made up of mudstones, which are very fine-grained red, muddy, clay-rich rocks, and halite, which is rock salt. This mix of mudstone and salt makes this rock particularly interesting because both have very low permeability. If a rock has low permeability, it's either very difficult or it takes a long time for fluid to migrate through it. So that offers us the isolation and containment properties which Fiona spoke about earlier. To understand the distribution of the Mercian Mudstone Group, we've built a database of geological data over the Inshore Copeland area. This is a map of the whole of the East Irish Sea. You can see the Isle of Man, the Solway Firth to the north, and the Cumbrian coast to the east. All of the grey lines show the location of the 2D seismic data that we have. The black dots are legacy boreholes, which were drilled by the oil and gas industry or by other inshore investigations. The orange polygon is the outline of the 3D survey area that NWS commissioned in 2022. The red polygon is an outline of a legacy oil and gas survey area. When we put all these data together, we build a database across a really wide area of the East Irish Sea. And this means that we can build a more confident interpretation of the 3D seismic area, and we can start to understand the geology of the Inshore Copeland area specifically. Using the database shown on the previous slide, we've created a regional interpretation of the base of the Mercian Mudstone Group, and here is a 3D image of it. This map is looking from the southwest, with the Cumberland coastline shown at the northeast of the map. The white polygon shows the area of the Inshore Copeland 3D Seismic Survey. The black dots and the lines show the location of legacy oil and gas wells. Our interpretation of the base of the Mercian Mudstone Group is colour-coded. The pink colours show the shallow extent of this surface, and the blue colours show the deep extent. Moving on from the 3D depth map, we can show you that same 3D surface but as a 2D map. The map on the right shows the depth to the base of the Mercian Mudstone Group over the Inshore Copeland 3D seismic area. The map has a scale bar to the bottom left, and we show the base of the Mercian Mudstone Group coloured in depth. The pink colours are shallow and the blue colours are deeper. The unfilled white polygons and the black lines on the map are the major regional faults in the area. By fault, we mean a discontinuity within the Mercian Mudstone Group. You can see that there are a set of faults to the west of the 3D survey and another set of faults to the east of the 3D survey, but the main inner area is relatively unfaulted. We've said previously that the depth search zone for a GDF is somewhere between 200 and 1,000 metres below surface, as defined in policy. And from this map, over the 3D area, we can see that the base of the Mercian Mudstone Group is between approximately 300 and 1,000 metres below surface. The next map shows the thickness of the Mercian Mudstone Group from the base up to the top. The top of the Mercian Mudstone Group is the base of the Quaternary section. Again, we're showing the same kind of map here, same scale, same area. The blue colours are thinner and the darker brown and purple colours are thicker. Over the Copeland 3D area, we can see that there's somewhere between about 300 and 800 metres gross thickness of Mercian Mudstone Group. And so both the depth map, which I showed you previously, and this thickness map really support the assumption that we've made that potentially suitable geology is present within the Inshore Copeland area. So what I'm going to show you next is a cross-section through the Copeland Inshore area. So I'm going to take a line of section through the 3D and extending up towards the coast. So let's have a look at that. So this slide shows the cross-section as we've described. The section is a slice through the earth showing the rock types, and it is derived from the seismic interpretation. The section x-axis is in meters, so you can see that this line is about 25 kilometers long in total, and the y-axis is in depth. So in this section, the line goes from 0 at the sea surface down to about 1200 meters depth. The section is coloured by rock type, so we can see that the shallowest geology is the orange Quaternary in this section. Below that in purple, we can see a relatively thick section of Mercian Mudstone group, and then below that in a pink colour is the formation below the Sherwood Sandstone group. The near vertical black lines are faults, and we're showing with a dotted line the approximate position of the coastline on the section. The section in the west stretches from the edge of our 3D shown on the inset map. The section extends almost to Ravenglass, just onto the coast, and I'm really just showing this line so that you can see over the 3D area, as we said previously, when we look at the depth and the thickness maps, we see a relatively thick section of Mercian Mudstone group. Here we've also interpreted some of the inner formations within the Mercian Mudstone group so that you can see the layers of salt and mudstone. You can see the Mercian Mudstone group is dipping around 10 degrees on average to the west, and we can see some regional faults in the nearest shore area, and then some bigger regional faults at the edge of the 3D. But within the 3D area itself, the Mercian Mudstone group is relatively unfaulted. So that's a summary of the important work that we've done so far. What we are working on now is to try and populate this interpretation with some kind of rock property interpretation. We've got relatively limited inshore borehole data in the Copeland area. There are a few existing wells from which we can access Mercian Mudstone group rock material. We have two images here. The image on the left is core material from a borehole called 113292, which is an existing well. The image on the right is core material from another borehole called Gateway 1E, which is actually drilled to the south of Copeland, but it's still a useful analogue borehole. We've accessed some of this material, which is stored currently at the British Geological Survey, and we're starting to do some analyses to try and evaluate the principal properties of this rock. These rocks here include halite and more mudstone dominated sections, so we can start to try to understand both the halite and the mudstone properties. Okay, I'm now going to hand you back to Fiona to talk about the considerations for future investigation.
As you can see on this illustrative example of a GDF, with the subsurface in the inshore area, we will carry on investigations covering the potential surface site, the access route for the waste, as well as the subsurface part deep underground where the waste will be placed. We hope what you've seen today explains why evidence so far demonstrates that there are potentially suitable rocks for a GDF in the inshore area of Copeland. As our investigations continue, we'll endeavour to provide further updates on our progress.